So in the last class, we talked about the integrals, and we said one way to evaluate an integral was to find the antiderivative, right? So basically, the antiderivative is the function which, when you find the derivative, you get the original function. Okay? That's what we did here. So today, we're going to talk about another aspect of it. So take a look at what I have here. I have d dx of the integral from a to x f of t dt. Let's just talk about that for a minute. Look at this one. I have the derivative of the integral. Well, last time we said integral means antiderivative. And now I'm taking a derivative of the antiderivative. So what am I getting back? The original function. Except, look at what happens. The function here, the integrand, what is inside the integral, is f of t. What's the variable there? It's t. But now I have my limits going from a to x. And when I take a derivative with respect to x, yes, I get the same function back, but what happened to the derivative? I'm sorry, what happened to the variable? It changed to x, right? So I started out with the integral of f of t. The variable was t. I integrated from a to x. I took a derivative with respect to x. And now I got the original function, but the variable changed from t to x. So now, if I have it written this way, that the derivative of the integral is f of x, it means, right, if I took an integral and then I took a derivative and I got the same function back, it means that the integral is an antiderivative. Okay, so now, suppose f is the antiderivative of little f, right? So if I integrate little f, then I do get big F, right? Yeah. F of x plus c. Okay, now, for the case of simplicity, right, for the sake of simplicity rather, look at that integral from a to x. I'm going to make it so that it's not a to x, but a to a f of t dt. So just concentrate on this left-hand side for a minute. If I have a to a f of t dt, what's a to a of the integral of anything? It's 0, right? So that left side becomes 0. And then what happens to the left side? If the upper bound is now a instead of x, then this becomes f of a plus c, right? So two things have just happened here. One, look at this. When I was integrating from a to x, I got capital F of x. Now when I change the upper bound to a, now I got f of a plus c, right? Instead of f of x, I got f of a. Now, what also happened when that upper bound became a? This whole left side became 0. So now, if 0 equals f of a plus c, then what is c? C is negative f of a. Okay, now, going back to this function up here, okay, when I had done a to x f of t dt, I had gotten f of x plus something c. Well, now I know what that something c is. What is c? Negative f of a. So then the integral finally, from a to x, f of t dt is f of x minus f of a. So it's the antiderivative evaluated at x minus the antiderivative evaluated at a, right? So this is the antiderivative evaluated at x minus antiderivative evaluated at a. Here, I can do it this way. Minus this, okay? So that's how we do a definite integral. All right, so let's put it all together and let's do one here. This is, it says evaluate the integral using the antiderivative of the quantity, using the formula, blah, blah, blah. So here we go. I have 0 to pi. This is a definite integral now. I have 0 to pi sine of x dx, right? What I need to do here is, this is going to be equal to the antiderivative. What is the antiderivative of sine of x? It's negative cosine x. So this is negative cosine x. Now normally, if this was an indefinite integral, like on the homework, without the 0 and the pi, we would have said negative cosine x plus c, right?
How do you know just by looking at that problem that you're looking for? Because it's a 0 to pi.
You know it's a definite integral because now I have upper and lower bounds here, whereas before I know. Okay, so look at this one. This just had the integral, right? These just had the integral. Now this has the integral here, but also from 0 to pi. Okay? All right, so now, before we would have said negative cosine of x plus c. But now this is a definite integral. So the way we do it is, this is negative cosine of x, vertical bar like this, which means evaluated at, or from 0 to pi. Now, you plug in the upper bound because it's capital F of the upper bound. So negative cosine of pi minus negative cosine of 0. That's how you do a definite integral. And now this is negative cosine of pi is positive 1 minus pi is negative 1, but there is a, oh, I'm sorry, minus negative positive 1. Sorry, so this is 2. Okay? All right, let's do another one. Here,
Oh, yeah.
okay. What we need to do here is find the antiderivative. So that's 3x cubed over 3, which is what? X cubed. And that goes from negative 1 to 2. So this is 2 cubed minus negative 1 cubed. So that is 9. Let's take account of what we have found. This is 3x squared, so it looks like this, right? We want the integral from negative 1 to 2. So basically, it's this area that we want. One thing, having graded your quizzes, the integral is the area from where to where, between what and what? between the curve and the x-axis, between the curve and the x-axis. So it's not this area here. No, it's from the curve to the x-axis. All right. This one, it's gonna go, okay, so this is negative x to the negative 1 over minus 1. So that is, and it's gonna go from 1 to 2. So that is 1 over x from 1 to 2, 1/2 minus 1, negative 1/2. Okay? Questions? All right. Look at this next one. What's the antiderivative of secant squared? Tangent, right? Tangent x. You are looking for a function, the derivative of which is secant squared, and that's tangent. And that goes from 0 to pi over 4. So this is tangent of pi over 4 minus tangent of 0. Tangent of pi over 4 is 1 minus 0, 1. Okay? You know what? Let's see how this actually works. Let's do a simple case. All right, let's tie it back. So remember, don't ever lose sight of what it is that you're doing, right? How did we start this whole integral process? At the very beginning, it was area. Is that right? It was area, and that was it. It was just plain old area. So imagine if you have y equals x, and you wanted to find the integral from 1 to 4 of x dx. Graphically, what does that look like? That looks like this. And then I want to go from 1 to 4. So that is the area that I want, right? Okay. What does the math tell me? That this is going to be x squared over 2. Oh, sorry. Evaluated from 1 to 4. And that's going to be 4 squared over 2 minus 1 squared over 2. What's that? 15 over 2. Okay? What do I get from the area? What's the y value here? 1. What's the y value there? 4. So what shape is that? It's a trapezoid. So it's half times the height. At least you didn't say circle. What's the height of this trapezoid? 3 times base 1 plus base 2. Okay, 1 and 4. What is that? 5 times 3, 15 over 2, guys. You see that? It's the same thing. But one you're doing it graphically, and you can only do it because it was y over x, and you did get a trapezoid and not a triangle. You could do it with a triangle too, right? But for one like secant squared, right? What shape does that give you? Nothing, none of the geometric shapes. So you have to have faith in the math there, right? Okay. Okay. Average value or mean value. Boy, have we seen that before? Yeah. Yes, we have. We have seen average value before. That was not for integrals, right? It was with derivatives. So the average value of a function, if f is integrable. Remember before it was always if f is differentiable. Well, now it's if f is integrable. If you can take an integral on a to b, then its average value on a to b is given by this. So this is 1 over b minus